Okay, well, anyway, Carlo, we were happy to have you here, and we're looking forward to your talk. And I understand you're going to tell us where information comes from. Go ahead.
Thank you very much, and thank you everybody for being here and listening. Okay, so the meeting is about the informational universe, and I thought to about presenting a number of works, a number of results that on which I've worked recently, which are right on the topic of the role of information around us in the universe, and specifically this question, the question of the title, where does information come from? I will get to this question through by asking the role of information in some peculiar phenomena where information is involved, phenomena that are strongly related to the direction of time. So this talk is essentially about the direction of time and how information interferes with the question of the direction of time. Just to be clear, there is no quantum, but I think everything I'm going to say can be translated with just a little bit more complicated language in quantum mechanical terms, but it's going to be a little bit more complicated, so I present things in classical terms. I start from two questions. One is regards traces and memories. Memories are a particular example of traces. There are traces in the world in abundance. Traces are facts about the present that tell us about the past in a way that there aren't similar facts that tell us about the future. Of course, given the present, we can compute things in the past and compute things about the future. We can compute eclipses of the moon and the sun equally toward the past and the future. But we have much more information about the past, a huge amount of additional information about the past and in the future in the forms of traces. Picture photographies of us when we're kids. We don't have photographs when we're old. But this has nothing to do with us and our own specific memories. If you look at the moon, there are craters in the moon. This is a picture of a crater in the moon. And this is a trace of a meteorite that fell into the moon in the past. So it's a trace of an event that was in the past. Now, the existence of traces always puzzled me for a number of reasons. Why we have traces of the past and not of the future if the fundamental laws of the universe are irreversible, are dependent of the direction of time? What is it that has a consequence that we have traces of the past and not traces of the future, if the basic equation of physics are time reversal symmetric? And if you think for a moment, the existence of this enormous amount of information we have about the past, we don't have about the future. We know what we've done tomorrow. We know what we've done yesterday. We don't know what we are going to do tomorrow. Is what sources our sense that the past is fixed. So to understand why there are traces is understand why the past is fixed. So the question, how does this happen, and why we have traces and why we have only traces of the past? And so if you want, what is the source of the epistemic temporal asymmetry? The fact we know the past, we don't know the future. But this is strictly connected to information, because traces are information about the past. So they store information. And the question is, where does this information come from? Who put the information there? If you have some amount of information, if you know something about the past out of some possible alternatives, you have some information. Where does information exactly come from? The other question, the second question I'm going to address, it's sort of a reverse of this question, and it's about the future. We can decide about the future. I can decide what to do tomorrow, and I cannot decide what to do yesterday. So this is what gives us the sense that the future is open. There are many possible futures, but there aren't many possible pasts. There's only one possible past. So this is the picture we have with one past that sort of can branch in a sense to our different futures. And there is something that happens, we make a choice. So why is this compatible with the deterministic laws of classical mechanics, with probabilistic laws of quantum mechanics, both of which are time reversal invariant? But even if you forget quantum mechanics, where the discussion might be more subtle, just in the universe at our scale is well approximated by classical mechanics, how is it possible that in a classical mechanic universe we can make choices about the future? What happened from the physical perspective, from the physical point of view? Of course, a choice is a complicated things that happen in our brain, whatever you want, but still, from the point of view of a physicist, how come that the same past history can evolve in different future histories? Or in other words, what is the source of the agency temporal asymmetry? The previous slide was about epistemic temporal asymmetry. This is an agency, the fact that you can act and affect the future and not the past. And once again, this is strictly related to information, because every time we choose, suppose we have a choice between two alternatives, one of the two is realized. So from the past, we didn't know which one of the two is realized. After we know which one of the two is realized, so we have one extra bit of information. So for choice, generate information. And again, where does this information come from? So these are the two questions that I'm going to address. Where does information come from when it's stored in traces, and where it's generated by choices? And this is the topic of 3 articles that I've written in the last couple of years. The first is about trace, the second about agency, and the third, it's a sort of overall perspective that connects back to the work of philosopher Reichenbach, a beautiful book that he has written on these topics. As always happened in these cases, I was super happy of having discovered some great deep mystery of the universe, and then I realized that these have been discussed before, and in particular beautifully discussed, but in a book of Reichenbach. So I connected to Reichenbach's picture. I realized that many similar ideas were already there. Other were sort of refinement of his views. So let's go to business. First, traces. This is a previous transparency. Traces, memory of information of the past, where it comes from, why the past is fixed. Now, the key consideration is the following. There are traces of the past, but the fundamental physics is time reversal invariant. So how can the phenomenon of traces be time-oriented? Well, of course, we know that the macroscopic world is full of time-oriented phenomena. All macroscopic time-oriented phenomena are time-oriented, they're reversible. That's what macroscopic thermodynamic statistics is all about. And we know how to understand it. Of course, there are open questions. I'm not going to enter into this open question. I'm going to take what we know, namely that if we assume past low entropy, so if you assume that the macroscopic state of the past was special in the sense of having low entropy, having a small number of microscopic state corresponding to it, plus statistical genericity, we get irreversibility, as everybody, we all know, having studied sort of thermodynamic and statistical mechanics. So irreversible phenomena in the world are thermodynamical statistics, and therefore they depend on the fact that we use a macroscopic description of the world rather than a microscopic one, and the fact, contingent fact, or if you want the fact to be understood, that entropy was low in the past. The entropy of this macroscopical coarse-graining was low in the past. Therefore, necessarily, traces are macroscopic phenomena. Traces can only exist thanks to thermodynamics and statistical mechanics as macroscopic phenomena. It took a while for me to digest that, and I tried hard to model traces mechanically, and it's impossible. And in fact, if you analyze any possible thing that you can call a trace, you would realize that there is some dissipation. So I'm not going to example, I just give it as a strong fact. Traces require dissipation, and therefore they are oriented by standard thermodynamical irreversibility. Now here is the hard result, and which brings clarity to the existence of traces. There are essentially 3 simple conditions, or 2 conditions, depending how you count them, which are sufficient to generate a universe with a large number of traces of the past. And the conditions are two. One is to have essentially low entropy in the past. So an imbalance, a disequilibrium in the past. And that's not sufficient, of course, because in a gas that expands and thermalizes, there's no traces that, that happen at all. So there is a second condition, which is the key one, which is long thermalization time. If your universe, or the system you're considering, is made by sub-components, by subsystems, which interact weakly, so the thermalization time is slow, this is sufficient for generating traces. This is essentially a theorem and was proved in my paper. The ideas, as I said, can be traced back to the work of Reichenbach. And to give you an example of how it works, just consider a super simple model, sort of mechanical model. Imagine that you have two kinds of degrees of freedom, some fast, hot degrees of freedom, which are represented by these red little balls here, zooming around very fast. Suppose we consider them as microscopic variables, so we know their average speed, which is their average energy, which is their average, which is the temperature of the system. And suppose that there is a colder system represented here by the blue balls, okay, which are some penduli, imagine, which are hanging there, whose average kinetic energy is lower than the temperature of the red gas. And moreover, that they're weakly coupled thermally, energetically, weakly coupled to one another. Now, this is sufficient to generate traces. You see, the only thing you have here is a system of blue penduli and a hot gas in equilibrium, out of equilibrium in the past. And then, of course, what happens is that because the coupling is weak between the two systems, once in a while, and only once in a while, one of the red little balls hit the pendulum, it starts oscillating. So if you take a picture, at one moment of the history, you see one pendulum oscillating. It still hasn't had the time to thermalize with the other. And its oscillation is a trace of an event in the past, which is the fact that it's been hit by one of the hot molecules. As soon as the average temperature of the kinetic energy of the penduli and the balls are the same, there's no trace anymore, because it doesn't tell you anything, the fact that, that one of the blue balls was oscillating. So here you see how traces are formed. And if you think about a photograph, a crater in the moon, step in the sand, a memory of you, it's always this situation, an imbalance, a thermal imbalance, which brings some energy from the hot system to the cold system. And then the energy remains sort of stored in a subsystem again because of long thermalization time. Long thermalization time is the key here. These are all processes that happen in a universe which doesn't run fast over equilibrium because there are long thermalization time, because the system is quite isolated. Now, this can be put quantitatively, and you realize here's where information comes about. Think back what happened. I go back when a little ball hits a pendulum. Some energy goes from the hot system to the cold system, right? So this is a passage of energy from the hot to the cold, which raises some, is dq, with some temperature T, so there is some entropy increase. So the phenomenon that generates the trace raises the overall entropy. And you can compute this. And in fact, if you, this allows to understand where the information comes from. The information comes from the fact that the entropy has raised. The entropy is negative information. So the low entropy means more information. So the entropy goes up, you lose sort of microscopic information and you gain macroscopic information. So traces are a mechanism that transform free energy, low entropy, into macroscopic information. And if you do the things quantitatively, you can compute the amount of information that is generated just as a function of the thermodynamical parameters of the system I've described, the difference of temperature, the temperatures, the heat capacity, and the thermalization times, the long thermalization times. So here we understand where the information of all the memories that is around is originated from the low pass entropy, just from there, okay? And therefore from the imbalance between the scale factor of the universe and the thermalized matter, which is the original thermal imbalance that generates the entire entropy growth of the universe. Then we go to the second phenomenon. How do choices affect the future? First of all, it's exactly the same picture as before. It's a very similar picture as before. How is it possible, mechanically, classically, that the future is split? Well, it's very simple. Once you realize that choices is a macroscopic phenomena, nothing prevents a macroscopic single state to branch, to have the possibility of branching into different macroscopic states, because each macroscopic state, it's a combination, it's an alternative, it's a set of possible micro states. So the past macro state is made by many micro states, some of which go up, some of which go down, some of which go straight. So there's no mystery into the split whatsoever from a physical point of view. But this shows that choices are a macroscopic phenomena, a thermodynamical phenomena, because they are irreversible. That's by definition of what they are. So they can always be described in terms of macrophysics, or more precisely, when we talk about choices, we talk about the macrophysics. Agency is a phenomenon which is macroscopic, which raises entropy, which is impossible without dissipation. Your brain is hot when you decide, you mumble, am I going to marry that girl or not? You make heat in your head. So choices are a thermodynamical phenomenon. And if you think for a moment, the picture I've given of the formation of traces from the point of view of thermodynamics and mechanics, from the fundamental point of view of physics, it's very similar to the picture one can give of choices. Because again, you have systems of the different, you can view this as a system of different temperature. The high system temperature is the agent now, the environment is a low system temperature. And the agent sort of brings down some energy, raising the entropy, because the energy goes from the hot to the cold, and raising the entropy is exactly what gives the possibility of picking up some of the free energy of the macroscopic state of the past, which was not in equilibrium. That's the point. It was formed by system, each one of the equilibrium, but that are not in equilibrium with one another because they're long thermalization times. And again, you go through the thermodynamics, you do a little bit of calculations, and the number of choices an agent can choose from, it's bounded by the thermodynamical parameters, the temperature of the agent, the temperature of the environment, and the value of the thermalization times. You get this beautiful formulas that connect thermodynamics with the information content of choices and information, which are the technical result of these papers. So once again, what happened in a choice is, of course, the fact that we don't know what happened in our brain, or if we know, it's not a choice. We just can reconstruct the mechanical process. But if we, to the extent we don't know what happened in our brain when we make a choice, or we don't know when a machine makes a choice because we don't know how it works, this not knowing, can be modeled into a separation of degrees of freedom between the macroscopic one that you control, the microscopic one you don't control. The split is because there are microscopic degrees of freedom you don't control. So the statistical fluctuations that determines what happened next. This is what gives the unpredictability of choices. So it's thermodynamics, it's ignorance of the details, and this is the main message of the talk and the connection with the title and with the role of information in the universe. Memory, it's a it's a mechanism that transforms the negative entropy, the low entropy, or the free energy, if you want, into information. And free energy and agency, the decision, the capacity of certain system to split the macroscopy, to take decisions, it's another mechanism that raises entropy, bringing up some information and transforming, once again, low entropy, or if you want, free energy, into information. And this is spectacular, in my opinion, because biology is all about information, right? DNA store information. Neural system works, collect information about the outside. We have senses, organs that collect information about the outside, and so on. With a proper perception, our brain knows about, get information about our body, and so on and so forth. And culture is all about information, and books are all about information, talks about our information, me talking to you about our information. So we live in this informational world, biologically and culturally. Where does information, this rich information, come from? It wasn't there in the past. There was no biology 6 billion years ago. There was no books and culture a million years ago. Where does information come from? From a perspective of a physicist, not from a perspective of a sociologist who want to know the details, from a perspective of a physicist. Well, it comes from the free energy stored in the fact that there is an energy imbalance, thermodynamical imbalance in the past. The universe was out of balance. Stars are irreversible processes that bring out, that raise the entropy of the universe. So from the sun, there is this flow of low entropy photons that brings all this free energy into on the Earth. And on the Earth, this free energy is all there available for doing, for coming up macroscopically into information and doing biology, culture, and all that. So all the information we are talking about when we talk about biology, culture, books, and everything, and the computers and the internet, is information that is sourced by the past entropy of the past. So from the point of view of physicists, there's nothing mysterious about it. It is a standard low entropy. Which means that is statistical and macroscopic in nature. Just very rapidly, I talked quantum classically. I never mentioned quantum mechanically, but to sort of anticipate a possible question, does quantum mechanics modify the picture? I'm convinced that the answer is no, nothing at all. The same can be said quantum mechanically. There is some confusion, I think, in the roots of thinking about quantum mechanics in the people who think that quantum mechanics by itself breaks the symmetry under time reversal because of measurement, because of this, because of that. I don't think this is the case. Quantum mechanical measurement is irreversible. Any apparatus that makes a measurement and stores the information is irreversible, but so is classical measurement irreversible, as shown by Feynman, by Reichenbach, by Eddington, by many people. It's absolutely impossible to make a classical apparatus and make a measurement and store the information without dissipation, without reversibility. So the irreversibility of quantum measurement is just reversibility of measurement. It has nothing to do with the quantum. And quantum mechanics by itself, whatever interpretation you want to hold about it, or almost whatever interpretation you want to hold of this, unless you want to add by hand, is reversible. Probabilities work in the past and in the future. Given the present quantum mechanical maximal information you can have about the system, you're equally ignorant because of quantum indeterminacy toward the past and toward the future. And the reason you consider the past fixed is just because what I talked before, because there are traces, because there are, because of thermodynamically, we have reason to believe that the past, the present have a lot of information about the past. But this information is bounded by H bar toward the past and toward the future equally. So quantum mechanics nothing to do with free will, obviously, I think, for a person who reasons. Quantum mechanics does not modify the picture. I have just one slide about my article back to Reichenbach, because as I discovered, Reichenbach is a philosopher of physics who did a lot of interesting things, but toward the end of his life, he wrote this book that was published after his death, The Direction of Time. And I want to advertise the book by Reichenbach. It was written in the 50s and published after his death, because it was astonishing for me to see which great clarity he has about the direction of time and all that. I'm not going through the actual content of the book, which I've summarized here, but I want to make one point, just the first, which is that universe has a branch structure. This is Reichenbach terminology for what I've called the existence of long thermalization times. This is what characterizes our universe. Is moving toward equilibrium, but extremely slowly. In fact, it's not going to equilibrium at all. We are still extremely far away from equilibrium, sort of 14 billion years from the Big Bang, because systems got trapped into subsystems which are out of equilibrium with one another and slowly sort of thermalize, very, very slowly, taking billions of years. That's what gives the thermodynamic structure of the world, and that's what gives the direction of time entirely. So that's my last slide. I just conclude by repeating the main pointers. First of all, trace, which was a big puzzle for me for years and years. I've been puzzling, what are traces exactly? Well, they are macroscopic notions. No trace in a purely mechanical system. Traces only exist because we don't describe the system. We don't know the system all to the dynamic mechanical levels. If we knew the system all to its mechanical level entirely, we could equally predict the past and the future. There was no meaning of a trace. And they appear generically, that would have shown, and that's also what Reichenbach had intuition about, every time there is an imbalance, thermal imbalance in the past and long thermalization times. So generically, they're there. Choices are, which are attributed to free agents, exist in nature and are perfectly understandable in terms of macro-micro distinction. The unpredictability of choices is the unpredictability due to the macroscopic approximation. And choices and traces generate information. And this information generated in this way, is macroscopical information that is sourced by the information in the low entropy in the past. So all information in biology and culture is sourced by, if you want, the free energy of the photons of the sun, by the low entropy in the past. The key for understanding that is a thermodynamic, which is neither equilibrium thermodynamics nor the full complexity of non-equilibrium thermodynamics. It's this intermediate regime, little studied but simple, which is characterized by systems separated by the fact that they interact weakly. So they can be both in thermal equilibrium, but they're out of equilibrium one with respect to the other one. So there's a slow flux that takes a long time to thermalize that. Focusing on that regime allows suddenly to understand all these things. Quantum theory does not change the picture. And finally, the time orientation of agency, the time orientation of the epistemic time orientation, the fact we know the past and not the future, is not in the fundamental laws of physics, is statistical probabilistics and thermodynamics. It depends on the particular state in which the world is and the macroscopic coarse graining that we use to describe it. Thank you.
Thank you, Carlo, for this very nice and deep presentation with many ideas and undoubtedly also questions that can be asked. Go ahead. Yes. Maybe I can do that.
You mentioned that in quantum mechanics, there is not a big difference in comparison with classical physics. I would like to ask about, in quantum mechanics, particularly in quantum field theory, we have CP violating systems like kaons. Actually, in standard model, even electroweak interactions violate CP invariance. That means time invariance, which is encoded in Kobayashi-Maskawa-Kabibel matrix. How this can be explained in your view?
Yes. It's a common confusion when people talk about the irreversibility of the world for reversal of time. In reality, one should always say the irreversibility of the world under that flip of signs, which change signs to all what it has to change when you flip time, including charge and parity. So the world is invariant and given any history of the world, there is a possible realizable history of the world, which is back in time with reversal parity and reversal charge. That's what I'm talking about when I talk reversibility. People often have confusion. Some philosopher, for instance, at some point said that Maxwell equations are not time reversible, which every physicist would say, well, that's absurd, because the entire phenomenology of electromagnetism is time reversible. But what he meant is, well, wait a minute. If you take a solution of Maxwell equation and you read it backward in time, it's not a solution of the Maxwell equations. And you think about it, yes, indeed, because you have to flip sign of B, of the magnetic field, right? If you take t minus t, the Maxwell equation, you don't get the Maxwell equation, get something wrong. You have to also to flip sign of B, which is a sort of charge conjugation in electromagnetism. So time reversal invariance includes whatever you have to flip sign of when you want to see the movie of a real processes backward as an actual realized process. In other words, if you look at the world backward, automatically the charge becomes the anti-charge and parity flips.
Thank you. Yeah, there's a question, two questions there, but maybe go ahead.
Thank you, Carlo. That was a very nice talk. This is Juan.
Hi.
So I was going to ask you about the quantitative predictions that you can make from this theory. Can you tell anything about the recent past or the future, the near future of the universe?
No, I cannot, magically tell anything and tell you who is gonna win the war between England and Russia, which is coming. I don't read the future. The quantitative contribution of this is in these two equations. One is this one, and the other one is where is it? Sorry, I've lost it.
It's on the traces part, I think. Yeah.
Oh, here. It's this one. So these equations connect the amount of information with thermodynamical parameters. So if you, I can tell you that if you want to store in a memory a certain amount of information, by fundamental principles, necessarily, you have to have two things. You have to have a temperature difference between some system and some other system, and you have to have a thermalization times. So you have to have something that keeps you away from equilibrium, tau C, tau H, which enter in this formula here. C is the heat capacity, where tau C is the thermalization time between sort of the system which has memory and the system whose effect you have the memory about. So the connection between the photographic machine and you young, there should be a long thermalization time there, and the other one of these two parameters has to do with the memory system itself has to be screened by thermalizing with the environment. And there's a similar things about choices. So if you actually want to use this equation in concrete cases, you're always far away from this bound. I mean, this difference is much bigger than it was needed, and the thermalization times are much higher than needed. But this gives a fundamental bound to the amount of information that can be stored in memory, and the other one can be gives a fundamental bound to the amount of information that you can choose. You can have a system produced to in choosing. Whether this can be used technologically, I have no idea, maybe not, but I think they're fundamental equations.
Charles, yes.
Yeah, you said that a quantum analysis of this doesn't change the result, but when I have read people who have looked at Maxwell's demon, like Charles Bennett, and the reversibility of quantum computing, they have said, this is what I've understood, and that is the writing is reversible, but what makes the thing irreversible is the erasing. And you didn't say anything about that. I was wondering do you agree with that, or is that something that changes what you said about quantum mechanics not making a difference?
Oh, that's a very nice question. Yeah, there is a sense in which it's a very nice point. Yeah, maybe I should think about that in detail, but I think that the answer is the following. When people say that writing quantum mechanics is reversible, essentially what they mean is that quantum mechanics is unitary. So to the extent in which you can, keep doing things following the Schrödinger equation, you're not losing information in any sense. So in this sense, things is reversible. So which translate in the language that I've been saying, to the extent in which you do the microphysics, right, and not the macrophysics, there is no distinction between the past and the future. So remember, traces are those information we have about the past that we don't have about the future, similar, right? So the fact that mechanically you can compute the past and the future, that's not what they call trace. Erasing, it's a very specific, it's something in that sense, in the sense of the paper, the result you quote, is a very quantum thing. It's not something that doesn't exist in classical mechanics, and is, if you want, the fact, in the simplest possible way, that if you measure position, then you measure momentum, you're erasing information about position, period. Okay, or if you measure the spin in a direction, and then another direction, another direction, another direction, at the end of the day, you have a maximum information about the system, irrespectively of what happened before. So you have erased what happened before. So it's the ground of this erasing is this one. And this is a purely quantum mechanical phenomenon. Now, you're asking, well, wait a moment, this does break the distinction between the past and the future. No, it doesn't, because it works both ways. So if you know that at some time the spin was this in this direction, a previous time the spin was this in this direction, a previous time the thing was this in this direction, what do you know about the spin being, say, very close to the first measurement? Well, it only depends on the closest measurement and not the one far away. So if you want to know something in this direction of time, everything in that direction has been erased. If you want something in this direction of time, everything is erased. So I think I have to think about better. Maybe I'm wrong, but I think this is the answer to what you're saying. I think the results you're mentioning, like many results of similar kind in quantum mechanics, they're true, they're correct, but they have an analog, a time reversal analog. So everything goes to one direction, also in the other direction of time. You break the direction of time as soon as you bring in macrophysics, dissipation, and thermodynamics.
I want to have two more last questions. So we have one here, Stefano, and then you.
Yeah.
Yeah, very nice talk. Also linking to indeed computation. So if we think about time in terms of change, so in kind of process, applying an operator in steps, so each step moves times forward, then of course we go from an input to an output. So isn't the error of time determined by this input and output asymmetry, in the sense that of course we can make an operator that is the inverse and can rewind all the operation we did in a reversible way. But at that point, we are going back in time, but we are also going from the output to the input. So the initial condition is not the same as in the comparison we are making going forward in time. So I would think that if we would go backward to the input, but then move again at time less than zero, so yeah, below zero, then you gain, even going backwards in time, again, the physics that moves forward in time, but just in the other way. What do you think in these terms of kind of computational point of view? Because at that point, you break the symmetry with the input-output asymmetry.
Yeah, good. Yeah, I think the right way to view this, we've been agonizing about these questions. There is a recent paper with Andrea Di Biagio and Marius Christodoulou on these issues exactly. I think the way of viewing this is the following. Imagine that you're in a laboratory and make a series of quantum measurements, okay? For a period, for a week, you make many quantum measurements, okay? Then you take all these measurements and I give them to you, okay? So you're not in the laboratory, you just have these collections of quantum measurements. Now, since you know quantum mechanics, given some measurement, you can predict the probability of some others, obviously. Or if I give you many runs of the same things, you can check that the frequency approach to probabilistic predicted frequencies by quantum mechanics. Now this works in both directions of time. So you can take as input the past one and predict the future, or you can take as input the future and predict the past. And the calculation you do is exactly the same, and it's stronger than that. If I just give you the set of results, you cannot tell which one. If I don't tell you, I give you this set of results, but I don't tell you if the right order of time is this or this, you cannot deduce it from the measurement. So there is a arrow of input-output. Of course, the physics is its model. Physics is not what happened. Physics is if this, then that. But if this, then that, classically works backward in time as equal in time, right? If today the planets are in this position, given the Newton law, then in the past there was this eclipses. That's what we do all the time in computing past eclipses, like we compute future eclipses. Quantum mechanics works exactly in the same way. Given information at some time, it gives some information about the future, some information about the past. Classical mechanics give exact prediction about the future and the past if we have enough data. Quantum mechanics doesn't. Even if we have maximal data, it doesn't give full information about the past because there is Heisenberg predictivity, if you want, and the same toward the past. So yes, you're right. The quantum mechanics is formulated as an input-output. The mistake is to think that input-output necessarily it's the orientation of time, which is natural for us toward the future. Why is it natural for us? Because of course we live in a macroscopic irreversible world. We know the past because of what I've talked about. We have this epistemic asymmetry. We know a lot about the past and we're interested about the future. We're not so much interested to use quantum mechanics to predict the past. It's much easier to look at traces. It's much easier to ask your friend what happened yesterday than to do a quantum experiment to predict what happened yesterday. Nobody would do that. So we use quantum mechanics toward the future almost always. And so we naturally think of quantum mechanics as predicting the future. So we naturally, because of thermodynamics, because we're immersed in an entropy gradient, and because we are natural beings that live in time, our brain has memory of the past, anticipate the future. Because of that, we use quantum mechanics to automatically identifying input with past, output with future, but nothing in the fundamental classical theory, mechanical, or quantum theory, mechanical, forces us to identify input with past and output with future.
Thank you. Do we still want to ask a question? We also have a discussion coming up. Isn't that all right? All right, so that's the last question for I think.
Okay.
Thank you, Carlo, for joining in our conference. Great. I have this question. Can you hear me?
Yes, yes.
I have this question since in the Powers of Two book, right, we go along on the ladder from bits to the cosmic ray background from power 2 to power 246 or to 56 to power 400. And in this work, actually there was a definition or a working hypothesis emerging. What is information, right? Which is after all what we're talking about. And the emerging hypothesis was that that information only exists when it's being copied. And you can apply this almost to everything we see around us. And so I was wondering if you make this statement, if I make this blunt statement, information only exists when it's being copied. How would that relate to what you're posing here? Thank you.
Well, information is a pretty generic name that can be used in different manners. There are.
Sorry to interrupt. In view of the time, I didn't say that. Of course, let's park knowledge. Let's not talk about knowledge, but only really about information.
Yeah. So if the sound was a bit confused, so I hope I got your question right. If by information you mean the fact that given a system, there is a description of this system, and this system is what you call, and this description is what you call information about the system. You know, the way we talk about information when we say unitarity is preservation of information if there is evolution in time and things like that. This is a different notion of information. I was focusing here on the notion of information that we have when we use macroscopic description of system, which is the one we use when we say there is information stored in a memory of a computer, or when we say in biology that the DNA has information. We're using a sort of higher level of notion of information. This is relative information, so it's not information which is a system. It's information that is between two systems. For me, the clearer and most useful notion of information. It's the one of Shannon, but not the one of Shannon in page 1 of his book. The one of Shannon on page 10 of his book, which is relative information, which is essentially correlation. A system can know about another system, can have information about another system, means, according to that Shannon's second definition of information, simply the fact that there is a constraint between these two systems, so that the two together can be in less states than the product of the state of one and the state of the other. So say they can be both like that, it's a constraint, and then you say that one has information about the other one, because if you look one, you know about the other one. So this kind of information is relative information, a system that have information about something else, okay? And that's, it's not something that only exists and can be copied. That's something that forms, it's produced, is lost, depending of the forming of, or breaking of constraints between systems.
Right, thank you. In view of the time, let's thank Carlo once more for a very nice discussion.